Hi, hello. Welcome to section 7 of chapter 7. As you can see, I'm really happy that it is the last difficult section of this chapter. And the next one, we have 7.8 as well, but it just, comparative discussion. It's more like discussion rather than section. So I'm finally so happy that we are here. I cannot mind my, I cannot hide my happiness. I cannot even say hide. So let's discuss this molecular orbital theory. I'm even crying with happiness. I don't know, or maybe it is because late night. Well, I decided not to go home until I'm done with this chapter. So I took my time and came back here. Let's see. So in this section, we are going to discuss molecular orbital theory. And this is the most accurate theory of all theories. And that's why we are going to pay attention to it and learn about it so that maybe in future, if you come across, you would know what it is. Let's see. But in this, general chemistry, we don't go super extinct into it. We discuss, reasonably for a few molecules, relatively simple molecules. But this theory is the most accurate theory to identify bonding, to identify structure, to identify molecular existence of all. Like, if you go to higher chemistry classes, maybe let's say a higher level physical chemistry class or higher level organic chemistry classes, you would come across this theory. That's where you will get more focus on it, but you don't come across this again in organic chemistry also. Just, something that we discuss now, and maybe only hardcore organic chemist that is going to come across these topics again. I did have taken these classes on molecular orbital theory exclusively one full semester in my master's when I did my master's in organic chemistry. And I did had an opportunity to take these classes again in the PhD, but I didn't have to because I have already taken a couple of those classes in my master's. So this chemistry is discussed under pericyclic chemistry, if at all any one of you is interested to dig more into this. Very fascinating stuff, very complicated, very tricky, complex, but very fascinating stuff. All right, let's discuss what it is. It's enough introduction, right? So what we discussed so far in this chapter is in the last chapter also, we discussed Lewis structures, and we also discussed valence bond theory, and we discussed hybridization of atoms. And we're still complaining because there are some things that cannot be explained by any one of these theories that we discussed so far. One of these is magnetism. None of the Lewis structure, valence bond theory, or hybridization doesn't correctly explain the magnetism of the molecule. So that's one thing that we want to know, if a molecule is paramagnetic or diamagnetic. For example, oxygen is paramagnetic, but according to Lewis structure or valence bond theory, you cannot actually tell that it is paramagnetic. What is paramagnetic is atoms in a molecule have single electrons. But just by looking at the structure here with all the paired electrons, you would think that no, it is a diamagnetic, which is misleading. That's why this theory has a little bit shortcomings. They were highly useful, like Lewis structures and valence bond theories or hybridizations. Hybridization is somewhat helpful in predicting the paramagnetism, but at least Lewis structure and valence bond theory are not unable to explain this. So there is one reason. So we are trying to make a case to learn molecular orbital theory here. Oxygen not able to explain paramagnetism is one case. And another case is, nitrogen is actually diamagnetic, but our Lewis structure doesn't tell. Our valence bond theory doesn't tell that it is diamagnetic, because according to the hybridization of N2, remember when we practiced N2 hybridization, if you draw it, you would come across, because N2 has nitrogen-nitrogen triple bond, you would come across each nitrogen having two single atomic orbitals, which means it must be really strong, really strong paramagnetic. But according to studies, according to the nature of nitrogen, nitrogen actually diamagnetic. But hybridization is leading us to believe that nitrogen is paramagnetic because it is showing single electrons on the atomic orbitals in nitrogens. So there is some, inconclusive evidence about the magnetism. So that is when we start making a case for molecular orbital theory. So according to molecular orbital theory, you could explain magnetism of a molecule. You could explain if it is going to be having a paramagnetism or a diamagnetism. Paramagnetism is one that is magnetically active, and diamagnetism is the one that is magnetically not active, if at all you were wondering. So let's dig into this molecular orbital theory. Let's learn what it is. In molecular orbital theory, you would use the individual atoms atomic orbitals and combine all of those atomic orbitals to mix and create a new molecular orbitals that belongs to all of the molecules. And according to this theory, you can explain the bond order, which talks about the stability of the molecule, and you can explain the magnetism of the molecules, and you can explain the stability of the molecules. I just said that twice. So here, again, let me repeat that because it's not easy to start if I say it just once. What is a molecular orbital theory is? It is a theory that combines the individual atoms' atomic orbitals to combine to form a combined new molecular orbitals for all the atoms that are present in a molecule. So instead of having like individual hybrid orbitals for each of them and then combine them to share the bonds, you would combine all of the atomic orbitals into one and combine only one I don't want to use that word. You combine all of the individual atomic orbitals to form one new molecular orbital set. Maybe it will make more sense if it is not already when I show you those at molecular orbitals. So what are the advantages of having these molecular orbitals is, they were somewhat similar to hybrid orbitals, but main advantage is that it can explain magnetism and bond order. Magnetism tells if it is magnetically active or not, and bond order tells if the molecule is stable or not. But other things like, having specific shape is same as kind of in hybrid orbitals, or, energies are kind of in same level as in hybrid orbitals. And each orbital, even if it is molecular orbital, still only accommodates 2 electrons, and electron filling of orbitals also follows the Pauli's exclusion principle, just like, in a hybrid orbitals. And how do you create number of molecular orbitals is based on how many atomic orbitals are available. All right, let's see how these molecular orbitals are formed. It is a little bit tricky to understand. Let me, I rearranged a couple slides. I got extra new information, try to help you guys to understand it better. So this is something that I want to remind you guys what we discussed in chapter 3. In chapter 3, we discussed that electron travels like in the form of wave, and wave has the nature of either undergoing the constructive interference where the same size waves collide into each other to form a bigger wave, or a destructive interference where opposite signed waves, instead of combining, they just cancel out each other by touching each other on wrong places. So here this is in phase where the throw is matching with the other throw, which helps to create a bigger wave. Whereas here a throw is touching another throw to cancel out each other to not have any wave anymore, so canceling out. So how we are going to use it is, we are talking about electrons around the nucleus, and we know that electron also travels in the form of wave, right? From the data of photoelectric experiment, Einstein theory and Planck's electron constant theory, all of these helped us believe that electron does travel in the form of wave, even according to Heisenberg principle, right? And Schrodinger principle. So when electron travels in the form of wave, and when you are combining individual electrons, individual atomic orbitals of atoms into one whole bunch of molecular orbitals, that is when different wave style of one atom will be exposed to different wave style of one atom. So we are talking about two different waves from two different atoms that are traveling, right? So when they are going to be combined to form a new molecular orbitals, there are going to be two possibilities. At one time, these electrons are going to combine to form a constructive interference. At another time, these individual atomic orbitals electrons are going to come across each other in a form of outer phase, in other words, to form the destructive interference. So just like how wave, double slit experiment where constructive interference creates that, light pattern, just like that. When you have, let's imagine, two electrons on two different atoms, just like hydrogen, and each single electron on each hydrogen, if you have two of them, are having their own wave function alone, right? But if you ask them to combine to form a one molecular orbital, now you have two electrons with their own two different waves that are going to come across each other to form a bond. In this case, at one time, it's going to form a bond in a constructive interference, which creates a bond, and in another case, it is going to create a destructive interference where it cannot able to create a bond. So we have names for it. So here you can clearly see that when two atoms brought together here, in the case of hydrogen molecule, here this is called linear combination of atomic orbital theory or method. So when these two met to each other, when these two met in phase, combined to form a in phase, we have a bonding. This is what we call a bonding. Individual atomic orbitals are combined to form a bigger wave of electrons where you can find the electron cloud most likely. This is called a bonding molecular orbital, this one. And also, when you form two atomic orbitals, you will form two molecular orbitals because one is in phase interference between two waves of electrons, one is out of phase interference between two waves of electrons. That out of phase interference result in oppositely signed electrons to come across each other because of this oppositely signed wave come across each other. As a result, you will have a area here. You see the line here? You will have an area here where you find no electrons. That is what we call it as a node. So as a result, in your second molecular orbital, you have a node in between two individual atomic orbitals trying to form a molecular orbital. Again, when you try to form two atomic orbitals, you will form overall two molecular orbitals, and one is as a result of in phase, just like in this image, you will form a larger molecular orbital compared to the size of starting atomic orbital. In another case, you cannot find a molecular orbital that is sharing electrons between them. Here, sharing electrons is difficult because they have a node and they cannot share electrons combinedly. They can still hold the electrons in those individual atomic orbitals that we now call as molecular orbitals, but because of the node in between, how we got the node? Because positively signed is trying to interact with the another positively signed that you got as a node in between. So you have this anti, which we label it as anti-molecular orbital. Because they were able to form bond in the bottom, you can call the bottom one as a bonding molecular orbital, and you call the top one as the anti-bonding molecular orbital. So another thing you need to know is, when bond happens, they happens because they were stable. So when atomic orbitals combine to form molecular orbitals, you have a bonding orbitals where it is in lower in energy compared to the atomic orbitals. See here, higher in energy and lower in energy. So bonding molecular orbital is lower in energy compared to antibonding, and antibonding molecular orbitals are higher in energy compared to atomic orbitals. Right? So similar to this is how you will form different molecular orbitals. So this is just what we just saw in this picture. When two s orbitals tries to form molecular orbitals, they form a bonding molecular orbital and they form a anti-bonding molecular orbital. Okay, it is for 1s orbital. And if you happen to have a, or 1s and 2s orbital, same thing, because similar shape, right, circular. So when you have a p orbital that is trying to form a sigma bond, now you can form a sigma bond with a p orbital. So p orbitals can participate in bonding with both in phase and out of phase. And here the first one is happening in phase because similarly shaped orbitals are interfering with each other. So you have a bonding molecular orbital here, labeling it as PO. And when you have oppositely signed orbital come across, you do not have a bonding because you have a node there. You label it as anti-bonding molecular orbitals. And other options are, these are, let's say, px, and when you have a py and py again, because py and py are pz same, they were just same. pz, they both are, you know, perpendicular kind of. So they both, when they try to form at once, they form a bonding molecular orbital pi bond, and when they try to form with opposite signs out of phase, they form a anti-bonding molecular orbital. So, you know, if it sounds tricky to you, I do not blame you. It's very complex information, and what we're trying to discuss here is like a gist of the large mathematical calculations of, you know, Schrodinger equations as a result. Like, that's why this is kind of mostly discussed in physical chemistry, where you need to do lots of math to come across these shapes and how their shapes are actually existing. So here we are kind of trying to get the extract of that information, summary of that information. So this is what you need to know. Now, if you did not get everything. According to molecular orbital theory, atomic orbitals combine to form molecular orbitals. Number of molecular orbitals are formed are equal to number of atomic orbitals are participating in bonding. So when atomic orbitals trying to form, because atomic orbitals contains electrons that revolves in a wave-like function, you will have a possible in-phase interference between two different waves of containing electrons, and you will have a possible out-of-phase interaction between two different electrons from the combined different atoms. So as a result, each single atomic orbital will have or will result in one antibonding orbital, antibonding molecular orbital, and one bonding molecular orbital. That's why a S resulting in two S orbitals. One is bonding and one is antibonding. And that's why a P orbital resulting in two molecular orbitals. That's why a P orbital resulting in two molecular orbitals. One of them is bonding, one of them is anti-bonding. So stick with me until I show you, you know, how the diagrams of these looks like. It gets easier from here. You know, I added all of these extra information just to make sure that you get the image of what I'm trying to say, because I just don't want to get by with simple words, because I'm not sure it, you know, it reaches you out. So let's work on a problem, right? What do we know about H2? H2 is the simplest molecule, you know, according to Valence Bond Theory, where we worked on H2 molecule, simply said that, you know, H2 molecules forms when the potential energy of two atoms is lower compared to individual hydrogen atoms. So each of the hydrogen atomic orbitals overlap over another to form the bond. That's what Valence bond theory says. So nothing wrong with the simple molecules like H2 with the perspective of valence bond theory explanation. However, molecular orbital theory can not only efficiently explain that, okay, H2 forms because it has a stable bond order, and also it can explain for other complex molecules as well. That's why we are trying to learn the molecular orbital theory. So H2 uses two 1s atomic orbitals of each atom to form two molecular orbitals. So each molecular orbital can take two electrons. So those two electrons will first in the bonding orbital. That is how H2 exists, and you can calculate bond order according to molecular orbital theory, and you can find if the number is non-zero number, you can comment on the stability. That's how molecular orbital theory has the advantage. And also you can comment on the magnetism of the H2. Again, I'm just going to review some of the information that came across again. What is a constructive interference is with respect to H2. A constructive interference result in a bonding molecular orbitals, right? As I've been saying, what it results in is it combines the individual atomic orbitals, I'm labeling it as AO, to form a bonding molecular orbital. You see, bonding orbital is one whole bigger than the individual atomic orbitals there. That's what happens when you combine the atomic orbitals, you form a bonding molecular orbital when they met in phase. But when they met out of phase, or in other words, destructive combination, destructive interference, they would form a out of phase with a node anti-bonding molecular orbitals. So the other possibility, if this is bonding molecular orbital, the another possibility is anti-bonding molecular orbital, where it does not have a shared electrons between two atomic orbitals shared by the atoms. So as a result, here you can see the node in between here. This is a node. So these are the two possible. So when you look at the whole molecule, you have a bonding, you have a bonding molecular orbital and anti-bonding molecular orbital. And we use the symbol sigma to symbolize electrons present in bonding molecular orbitals, and we use the symbol sigma star to symbolize the electrons present in anti-bonding molecular orbitals. Let's see what they mean, like bonding and anti-bonding molecular orbitals. Let's look at this example of H2 molecular orbital theory. This is how it would look like. So you have two hydrogen atoms. Each one of them has one electron in 1s, and two individual hydrogen atom atomic orbitals forms total of two molecular orbitals. So these are molecular orbitals. And the one that is lower in energy is bonding molecular orbitals, that we label it with sigma. And the one that is higher in energy than atomic orbitals is labeled as anti-bonding molecular orbitals and labeled as sigma star. Right? So how many electrons you have? Total, you have two electrons, and you start fill them in here. So you have two electrons in the bonding molecular orbitals for hydrogen. Let's use that. Let's see how we can use that. We can use it to calculate the bond order and comment on the stability, and comment if the molecule exists or not, and comment if the molecule is stable or not. This is how you would calculate the bond order. You would calculate the total number of bonding electrons, and you will subtract the total number of electrons present in the anti-bonding molecular orbitals. You will take it over 2. So if you use that formula on the H2 molecular orbital theory, you will have a 2 minus 0 over 2, which says that your bond order is going to be 1. Bond order 1 says that it is not 0, which means molecule exists and it is a stable molecule. H2 is a stable molecule. You would know because now you know for sure because you were able to calculate the bond order of a molecule using the molecular orbital theory. Now let's look at another example, He2. So He2 has two atomic orbitals. So it is going to create a total of two molecular orbitals. And each one of the H2 has 2 electrons in its atomic orbitals. So what it's going to do is it's going to use total of 4 electrons to fill from bottom to the top, according to Hund's rule. So you put 2 electrons in here first in 1s, you completely filled it, and you will go to 1s sigma star. You will put 2 more electrons because you have 4 electrons, so you have to fill from bottom to top. So when you do that and you count bond order, if you can count, it's going to be 2 minus 2 over 2 says 0. What it means is He2 molecule cannot exist. You can clearly tell that He2 molecule is not a possibility, and it doesn't exist because bond order is 0. If a bond order is 0, molecule cannot exist. It is one of the advantages of molecular orbital theory, where you can predict the stability of a molecule. Okay? So we are going to talk about here pi orbitals. I already show you how do they look like, but I'm just going to show you again before we work on a bunch of problems, molecular orbital theory diagrams. So pi orbitals, as I showed you previously, just like single orbitals, they have an option to form both the bonding molecular orbitals and also antibonding molecular orbitals. It's not even an option, it is given. Because electron travels in the form of waves. The electron is present in p orbital, let's say in px. One time it come across each other in the in phase, one time it come across each other out of phase. So as a result, it forms once a bonding molecular orbital from these individual atomic orbitals. In another case, it's going to form a anti-bonding molecular orbital, which you can see it here. I would say this is the antibonding molecular orbitals. There's the one that looks bulky and the one that looks smaller. That's a good indication to predict for pi orbitals. Another case is, you have p orbitals in different shapes. Let's say if your p orbital is in a perpendicular shape, then it would form the bonding molecular orbital and antibonding molecular orbital like this. One is looks larger, bonding one always looks larger, and antibonding one always looks smaller than the first one, and also they were not connected because they always have node in between them. Again, if you try to have a p orbital that is like not perpendicular, not horizontal, but kind of like tilted, like PC, then you will have a bonding and antibonding just like previous one. It is possible to have, again, for any orbital to have a bonding and antibonding orbitals. All right, we're almost close to the end of the topic. I have a few examples to show, then we are done. No new information. So in here, if you can see, we have a bonding order that results in a combination of both these sigma and pi orbitals of individual atomic orbitals formed by O2, F2, and Nu2. These are the bonding molecular orbitals diagram order from bottom to the top. This is how electrons gets filled in molecules containing O2, F2, and Nu2. And in this order, it is very specific. Sigma 2s first, followed by sigma star 2s, then sigma 2px, then followed by pi, and pi stars and sigma stars. Watch out because it is only exclusive for elements O2, F2, and Nu2 because they were bigger, larger elements, and they have specific, let's say, differences between the sigma of s orbital and sigma of p orbitals with the pi orbital. So pi orbital is kind of close to the sigma orbital of p orbital is kind of close to the s orbital of sigma. That's why it is this order. However, when you go to less electronegative elements like lithium, beryllium, carbon, and nitrogen, you will notice that the order changes. Instead of having after sigma star, instead of having sigma 2s, you will have pi orbitals because of size of the atoms is smaller and not much differences in subshell energy levels of sigma and pi orbitals of these elements such as carbon, nitrogen, boron, and lithium. You have these pi orbitals in lower level compared to sigma. So this order changes. This order is exclusive. This is kind of, you need to remember that lithium, oxygen, and fluorine, neon, oxygen, fluorine has a different molecular orbital priority compared to lithium, beryllium, or boron, carbon, and nitrogen. So we are going to use those bond orders, and we are going to use the usual rules to fill the electrons, like lower energy levels fills first, and then you will go to a higher energy level and you will put 2 electrons in each of the atomic orbitals before you move on. And you will use the Hund's rule, which says that you need to share electrons equally if you have more of the equal orbitals, equal energy levels orbitals. So here is the summary, the grand summary of everything that we discussed. So for you to understand everything going on here, we need to spend like half an hour to explain all of this topic in this lecture. But I hope it is totally worth it when you get all of this that we are going to discuss. So let's work from Li2. Okay, Li2 has, excuse me, one single electron in each lithium. Excuse me. So lithium has one valence electron in each one of them. They were in 2s1. So they were going to use each of its single atomic orbital to form a molecular orbital, and they are going to use all of its 2 electrons. It has 2 electrons, and it's going to start filling those 2 electrons from the bottom, starting from here. This is the order that we start filling electrons, and it will completely fill its 2 electrons in its first sigma 2s molecular orbital. Now, if you apply the bonding order formula, bonding order for Li2 is going to be 2 minus 0 over 2. So it says bonding order is 1. It says that Li2 molecule can actually exist. And let's pay attention to the bond lengths and bond energies as we're discussing more problems. So B2 has 3 electrons each in each of the borons, so which means it has total of 6 electrons to give it to molecular orbitals. So B2 has this order of sigma 2s star, then pi orbitals. So let's see what happens. So you start filling electrons from bottom, you use 2 electrons here, 2 electrons here, but because you have 2 more electrons, you need to give 1 here and 1 here. So you have a single electrons there. And if you count the bond order for B2, you have 2 electrons in antibonding and 4 electrons in bonding. As a result, you have bond order of 1. Okay. So now let's use the other data that we have. Let's compare bond length between Li2 and B2. Bond length is decreasing between Li2 and B2 because there are more shared molecular orbitals in B2 compared to Li2. And also bond energy is increasing in B2 compared to Li2 because there are more molecular orbitals connected to each other in B2. So hard to break the bonds away. And the magnetic properties, Li2 is diamagnetic because it has paired electrons, and B2 is paramagnetic because it has single electrons. So let's look into C2 and N2 together. Let's see what happens. We know that each of the carbon has 4 valence electrons, so there are total 8 electrons, and each of the nitrogen has 5 valence electrons, so total of 10 electrons to work with here. So you start filling from bottom. So for carbons, you have a completely filled pi to y and pi to x, but for nitrogen, you have completely filled sigma to px. So if you count the bond order, carbon has 2 and nitrogen has 3. What it says is that the more bond order, the more stable it is. Let's see if it is true. Bond energy is 627 for carbon. Bond energy is 941 for N2, which is true because it is higher bond order. Both of them are diamagnetic because both of them are paired. Again, you can look at the bond length. More bonds are connected between nitrogen, so shorter the length because it brings closer to each other compared to carbon. Okay, let's look into O2, F2, and Ne2 together. Each oxygen has 6 valence electrons, to a total 12 electrons to work with. Each fluorine has 9 valence electrons. So each fluorine has 7 valence electrons, so 14 electrons to work with. And each neon has 8 valence electrons, so total 16 electrons to work with. So we start filling from bottom for oxygen, fluorine, and neon. And remember, the order of sigma and pi matters depending on which element you're working with. For oxygen, fluorine, and neon, sigma 2px is in lower energy level compared to pi 2px. It makes a huge difference for magnetism and bond order, so you need to remember that. So if you start filling them, the highest occupied electrons for oxygen is single occupied pi stars, and highest occupied electrons for fluorine is paired pi stars, and highest occupied electrons for neon is sigma pi star. So using that, if you count the bond order, oxygen has 2, fluorine has 1, and neon has 0, which means neon 2 does not exist, but oxygen 2 and fluorine 2 does exist. And if you use it to identify bond length, fluorine happen to have a larger bond length compared to oxygen because oxygen is more stable and it has more attraction between them. And bond energies, the oxygen has much larger bond energy compared to fluorine because oxygen has larger bond length, and oxygen is paramagnetic and fluorine is diamagnetic. How do you identify? You look at the highest occupied electrons and see if they were single or paired. This is the grand use of molecular orbital theory. And what we are working here again are the very basic examples, simple examples, but you can apply this molecular orbital theory on any molecule. It is, even a large organic molecule or even an ionic compound on any molecule, you can apply it and you can identify its magnetism, and you can identify the bond order, and you can comment on the stability, and you can predict the bond lengths and the bond energies. You can do lots of cool things. Most importantly, you can tell if the molecule exists or not. Okay. All right. Let's look into this last example that belongs to this chapter and call it this section. So here, the molecule called superoxide ion, O2 minus, has implicated in a number of degenerative conditions, including aging and Alzheimer's disease. Using molecular orbital theory, determine whether O2 minus is a paramagnetic or diamagnetic, and then calculate its bond order. That is so cool. It is asking us to comment on magnetism and find the bond order. So I hope you start working on it before I show you the work and you check your work with my work here. So O2 minus, we could definitely use molecular orbital theory, and all you need to know is in which order molecular orbitals are present. In oxygens, you have right after sigma star 2s, you have a sigma 2px. That's all you need to remember. Okay, because the energy levels are larger between pi orbitals and s orbitals in oxygen, fluorine, and neon. That's why you have right after sigma s, you have sigma p first. So in O2 minus, let's identify how many electrons are in there. In O2 minus, there are 12 valence electrons from 2 oxygens, and with the minus, you have 1 more electron, so 13 electrons total. And if you start filling them from the bottom, you will happen to have in your highest occupied molecular orbital a paired electron and 1 single unpaired electron. Because I'm seeing unpaired electrons, I'm going to comment that this is going to be a paramagnetic. Here it is, it says paramagnetic. And if you try to identify the bond order, you will subtract the antibonding electrons from the bonding electrons. Here are the antibonding electrons. Wherever it says sigma star, there are 3 of them here, 2 of them here, and you contrast off the bonding electrons, and you will identify the overall bond order as 1.5. Here you just took shortcut because it only counted these electrons because these two cancel out each other anyway, right? Same, 2 minus 2, right? So 1.5, which means, it is a stable molecule. So that is how we use this information. Molecular orbital theory. It is again highly useful, but here we just lightly touch it. We just introduce you how it works. Um, uh, it's not going to be complicated, at least in the terms of how I'm going to test you, but to get it, sometimes it is challenging. I understand. Even some of my smart students sometimes did get trouble with it in the previous times. That's why I spend extra time. So I went different approach. I added a couple more things that I want to add to explain how it is actually in phase and out of phase, how it actually results in bonding and anti-bonding, all of that. I hope it pays off and you guys will get it. If not, again, we can always discuss in the class during the discussions. I will see you in next and final recording.